So last week, before our weekend, we talked about the effect of a current carrying wire that is placed in a magnetic field, and if that wire forms a loop, then the Lorentz force that exerts a force in one direction on one side of that loop, and in the other direction on the other side of that loop, then as a result, that loop will want to rotate. And when it rotates, we can ask questions like, okay, well, how fast does it rotate? So in order to figure out how fast it rotates, we need to work out what the force is that's acting on it. And the force, when we're talking about rotation, is described as torque. And then if you want to figure out how fast it actually accelerates, you'll need to know the rotational moment of inertia. Now that part's the mechanics part, so we skipped over that. We just said, okay, that's where you need to connect it to mechanics, which hopefully you've seen in Physics 225. But the torque part is the part of this class. So so we did two loops. We did a square loop and we did a circular loop. And today we will generalize this to arbitrarily shaped loops. And then also you'll find that we'll discover some stuff that you might have not seen coming yet. And I hope that you'll hang on to that cliffhanger moment until Thursday, when we actually describe what it is that we just discovered. And then so far in terms of Maxwell's equations, we've got Maxwell 1, which is Gauss's law. Maxwell 2, which is the circuital law that expresses that the electric field is a conservative field, right? Take a line integral through a closed path in an electric field. You're gonna get 0 if you come back to the original point. And then 3, which is Gauss's law for magnetism. And there are four Maxwell equations. So we'll need to get to number 4, and we'll do that right after. But we'll also find that we need to make some modifications to number 2 and even number 4, even though we will put it together in the very beginning. So we're not quite, we haven't really completed the picture yet, but we're getting very, very close to seeing what that framework of electromagnetism looks like. As I mentioned to you before, the beauty of electricity and magnetism, as far as I'm concerned, is that it's one of those first physical theories that allowed us to take a whole bunch of physical phenomena and sweep them all together and describe them in single coherent framework. And it's that process of unification allows you to say, well, I think we understand it better now, because you could have one law for what do magnets do when you place them in a magnetic field. You could have one law for how do electrostatic charges interact. But if you can all kind of put it together, you say, I think because we have a unified description for this broad class of principles, we have a better understanding of what nature is actually doing under the rug. So it shows its face in very distinct phenomena, but the fact that you can unify that all under a nice single unified picture is the power of this electricity and magnetism. So we'll do that, and then afterwards we will be done with this chapter. So that means get ready for chapter 4. All right. Okay. So before we generalize the torque on a motor, let's go over one more aspect. So remember, I was explaining to you how electricity and magnetism is the study of electricity and magnetism, and not only that, but also how they interact. Even before they interact, you can already start describing what they do if you have both electric and magnetic fields acting on something. So we have two force laws. So we've got our Coulomb force law. Coulomb force that says that we've got some kind of a charge moving through an electric field. This electric field, the origin is not due to this charge. Then this charge experiences this force, and that's the Coulomb force. So that's purely electrical. And then we have the Lorentz force. So also an F, also proportional to Q, except this is V crossed with B. And this is for a point charge that moves through a magnetic field B with some velocity V. And since they both scale with Q, it makes sense to kind of put them together and see what happens if you have both an electric field and a magnetic field and some kind of a velocity. So we can call this the Coulomb force and the Lorentz force by indicating that they have those subscripts. But let's see what happens when you have, what happens if you have both E and B fields. So then the net force is going to be the sum of these two. So it's going to be the Coulomb force plus the Lorentz force. So that's going to be QE plus Q V cross B. Now, if the velocity of this particle is 0, then this whole thing doesn't matter. But if not, then we start taking the magnetic field into account. So this is the force law for having both an electric and a magnetic field. So we can call it the Coulomb-Lorentz force if you want. Also, some people just call this the Lorentz force. Once you study relativity, you'll find that there's actually a way to describe this as a single force, where this thing shows up because there are funny things happen when things have speeds that are not 0. And it has to do with the theory of relativity. But for now, we'll just treat them as two linear terms that add up to give you net force. But to remember that there's a reason why they kind of show up together in this way. And this is something that you will learn in further semesters of electricity and magnetism. Okay, so let's take some kind of an example. So we'll have a point charge Q, and let's give it some speed, some V. Let's assume this thing is greater than 0, and we need to look very carefully at this. In order for this Lorentz force to do anything, we need to make sure that the magnetic field is perpendicular to the velocity. So the magnetic field would have to be pointing, for instance, either into the paper or out of the paper. So let's say let's call this the B field. So that's the B field. Okay. And then we also need an electric field, and I'm going to draw the electric field perpendicular to it. So let's see. Let's do the electric field. In the direction that is down. Okay, so that's the electric field. All right, so let's go over this. First of all, free body diagram. Free body diagram is always you take a force, and when it's acting on something, you draw the force as a vector starting in the point where it's acting on. So the most simple one is the force due to the electric field. And the electric field in this case is the red vector field. So that means that there's a force due to E, and it's acting in the direction of Q times E, and Q is positive, so positively charged particle. So that means, I'll draw this down. And you can, sometimes it's easier to just draw it as an F sub E, because the C and the L, especially if you start writing fast, they become hard to distinguish. So just do F sub E. Okay, so that one's easy. It's just pointing down. All right, now V cross B. V cross B is tricky because that's one of those cross products. So remember, there are 3 manners in which you can do your cross product. The first is the right hand rule. So my right hand, start with your fingers in the direction of Q times V. So that's like this. Then curve your fingers and point them in the direction of the magnetic field. In this case, that's into the paper. So that means I have to flip my hand like this. And now my thumb is pointing up. So that's my Lorentz force, or my F sub B, if you want to draw it like that. So FB. So that one's pointing up. That's with the right hand rule. The left hand rule, again, that's the one that I prefer. You start with your fingers in the direction of Q times V, so Q times V. And then magnetic field points into the paper, so you catch them in the palm of your hand. Your thumb is indicating the direction of the force. There you go, up. The other way to do that is to use a set up a coordinate system like a person. So there you go. So let's call this X, let's call this Y, and let's call that Z. Doesn't really matter which one you use, but as long as it's a right-handed coordinate system. So in that case, my F sub B, if you want, is Q V crossed with B. In this case, V is in this direction, that is pointing in the X direction. That's a positive X direction. And we're going to cross that with B. B happens to be pointing into the paper. That's the same as Y. So that's a B times Y hat. So Q, B, B. And now X cross Y is Z. So that gives you a Z hat. Z is pointing in that direction, pointing up. Okay. So that's the free body diagram. This is a very famous setup, and it's sometimes called crossed E and B fields, because you can see that E and B are perpendicular to each other, and they have to be perpendicular to each other because otherwise you cannot balance and see the way that the electric and the magnetic field compete. So in this case, there's an electric field that's pushing the particle down, and then there's a magnetic field that's pushing the particle up. And there's a balance between these two, and that's what we will do next. Is when is F net 0? Again, 0 vector is a little bit of a funny object, because how can something have a direction if it has no length? But okay. So that's the sum of these two, the net force, or the Coulomb Lorentz force. When is that 0? Well, Q E plus B crossed with B. The first is, well, Q is 0, but that's kind of what we call the trivial solution. We usually ignore that because that's a little bit like, we're not playing this game, because if there's no charge, obviously there's no Coulomb force and there's no Lorentz force. It's good to recognize that the net force is 0 if this thing is not charged. But I said that it was charged and it was bigger than 0, so that's a trivial solution, and also does not satisfy our setup. So, or E, oops, plus V crossed with B is 0. Now E was pointing down, so that's a minus E z hat. And v cross b is vb z hat, because we have calculated that here, vb z hat. All right. So we can factor out the z hat, and z hat cannot be 0 because it's a unit vector. So therefore, vb is equal to e, or v is e over b. So that's kind of an interesting situation. So there's one particular speed for which, if you have a charged particle and it's moving through a crossed EBU field configuration, that the net force is 0, such that the particle goes straight ahead. Now, so it goes this way. Now let's say I'm putting a little aperture here. So I'm going to draw a little opening. And if I make this opening small enough, that means that the only particles that will go in a straight line are going to be the particles that move exactly at this speed. And if it goes a little faster, then the Lorentz force dominates. So this thing pulls harder. So if it goes faster, it goes this way and it hits the screen here. And if it goes slower, it goes this way and it hits the screen there. Now, therefore, the only way that the particle can go through here is only if v is e over b. And otherwise, it is trapped. So that's what we call a speed trap. And this is a different kind of speed trap than you might find in the city. You know, the speed trap in the city just means you go over a certain speed, you get caught. So basically only one of these. This is a speed trap where if you don't have the gas pedal exactly at the right throttle position, you're not going to be able to make it through this hole. So different kind of speed trap, but it's called a speed trap nonetheless. Okay, so we have two situations. We have a v that's bigger than this velocity, or a v that is smaller than that velocity. So let's work out what that looks like. So we'll call this v, or we'll call this v naught. So v naught for the speed with which it needs to move in order to go through the aperture. Okay, so that's the aperture. So if the speed is some v naught plus some delta v, so delta v is the deviation from that ideal speed with which it needs to move through the aperture, then the net force, F, is still QE plus V, but now V is V naught plus delta V in the x hat direction, crossed with B, which is in the y hat direction. Gets a little bit more smudgy. I'm using a black marker today that gives better contrast, but unfortunately it's a little bit more smudgy. So this E is still in the Z direction. So we have a Q, E, Z hat, plus distributive property, V naught, X hat, crossed with B, Y hat, plus delta V, X hat, crossed with B, Y hat. Now, this term together with this term are going to cancel, because by definition, V naught is E over B. So if you put that in there, you put your E over B, you're going to get V naught replaced by E over B. So I'm going to replace this as E over B. Then that means you get E over B times B. So you have E, and now you have E times X cross Y, that's Z. So you get here an E z hat. So E z hat is what this term becomes, and we already have a, I'm sorry, I'm missing some Q's. We already had that, and I'm also missing a minus here, so it's a minus here. Okay, so this E z hat and this E z hat, they will cancel, and all we are left with is the effect of that extra little bit of speed. So we get a final speed, Q delta V Z hat, because B. So that's your, that's the net force rewritten. And now it should be clear that delta V, the sign of delta V, is going to tell you the sign of the force, because this thing is going to multiply Z hat B and Q and B aren't changing. We already said that we have a B field in some direction and we have a Q that is positive. So the only thing that's going to tell you whether the net force is positive or negative is the sign of this delta V. So therefore, there is a speed for which it goes, sorry, a delta V for which it goes up. So let me draw that here. So makes this kind of path. So this is if delta V is greater than 0, and it goes in the opposite direction, where delta V is smaller than 0. Okay, so let's go back to our rotating wire. So last week we had a setup where we were taking a loop with some conducting material. We made it square, and then there was a magnetic field placed in this direction, and there was therefore a Lorentz force acting on this segment, and then there was a Lorentz force acting on this segment, and this one was pointing into the paper, this one was out. So as a result, there was a torque because this thing was trying to do this. As a result, there was a torque that caused it to turn this way, and we were able to calculate that torque using this definition of D crossed F. And then, excuse me, it rotates around this part. So when we get a torque, the vector that comes out is the axis of rotation with a right-hand definition for the rotation. So put your thumb on the wire and then rotate it around, and then it turns. So did that part, and then and then we saw what happens when it turns, and we'll get to that in a little bit. And then we did this part, or rather, in class, I made an attempt, but I actually swapped these two terms. And one of you actually spotted that in the chat, so thank you. But I fixed it later. So let me go over it one more time in case you didn't see it in the video. So there is a differential form that we need to use for this kind of a setup, because there's no longer a straight segment where we can say over finite piece of length, there's going to be some kind of a form that's going to give rise to some kind of a contribution to the torque. So instead of using this IL crossed with B, we had to do a differential form. So we made it a, where did we go here? We made it into a D torque. And that means that we needed to, instead of using segments of big finite segments of length, we needed to use infinitesimal segments of length. That's the DL vector. And then that's where most of the work happens, is figuring out what that DL vector is. So that's also where I messed up. My X component in this case has to go with the sine phi, because it starts off pointing straight up if phi is the angle with the x-axis. And it has to go minus phi, because when phi goes up from the point where it starts pointing to the left. So the X component starts off negative, and the Y component, sorry, the Z component starts off pointing straight up. and that is a cosine phi. Another way to figure this out is actually use just this straightforward definition where you say, if I want to know what dl vector is, it's going to be whatever happens to the position vector if I take an incremental d phi and see what happens to that position vector. So you take the derivative of the position vector, where the position vector describes any arbitrary point on this wire as a function of phi, and that's just r times the regular form x cosine plus z sine phi. So take the derivative, sure enough, the cosine becomes a minus sine, the sine becomes a cosine, da 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 da. Okay, now when you then work out this product, you get this thing for the df, and the df you then cross with the arm. Now the arm that I used for this was actually the arm for the position vector. The cool thing is, usually you would say, I'm going to use the arm pointing perpendicular to the axis of rotation. And we know already from symmetry that the axis of rotation is going to be this z-axis. So therefore, anything perpendicular to this can only have an x component. So we could decide to throw away the z component. But the nice thing is that actually, if you don't do that, you'll end up with this product of sine phi cosine phi, which is an odd term. So when you take the integral over phi, this term actually disappears. So that's cool. So even if you don't know exactly what the symmetry of the situation is going to do for the torque, the symmetry will tell you exactly what's going to happen. So so this term disappears even if you put in that term to begin with, and you're only left with this one. So that's the integral of a bunch of stuff times cosine squared. Now the cosine squared integral, there are two ways to do this. You can use trig identities, or you can use this complex notation trick where when you square it, you just get those. Or you can do this this trick, which is super sloppy, but I know it works, so I don't have to remember much. So if you have a cosine, you square it. That means everything that's below the 0 line is going to flip up and go above it, and then you get something like this, and obviously it gets double the frequency. And the mean value is 1/2, so the area under the curve is going to be the mean value times whatever the width is, and the width is 2 pi. So 1/2 times 2 pi gives you pi. Outcome of the integral is pi, and then you get this thing. And you got, for the torque, IB times the surface area of the loop times z hat. So the thing I wanted you to pay attention to was the fact that this thing is proportional to the area. So now I want to look at these two terms. So for a square, you get BIL squared, and for a circle, you get BI pi r squared. So it's always of this form of B times I times the surface area. So let's explore why that is. So that means that we need to set up the problem a little bit like this, except we'll have to make the loop have some kind of a arbitrary shape. But we'll start the same. So we have we'll have some kind of a magnetic field. So that's our magnetic field. And then we'll take a wire, and the wire, I'm now drawing it as some kind of a wire with an arbitrary shape. Now, the current is still circulating in this manner, so clockwise. Sorry, counterclockwise. And the question is, what's the torque going to be? A couple of things about notes. So what we were doing earlier is we were saying, if you don't know exactly what the arm is going to be, you can trust that symmetry will help you out. But for simplicity, we're gonna remove that degree of freedom, we're going to assume that it's actually symmetric around this axis. You know, I didn't really quite draw it that way, but we will assume that that's okay, and then we'll just ignore the fact that it's not exactly symmetric. And we're going to assume that there's going to be some kind of a rotation. And the question is, what's happening to that torque? So the first part is going to be the same. We'll have to go from this finite length notation to a infinitesimal length notation. So that first part is going to be the same. So let me see if I can put this on the camera right next to each other, so you can see how things change, because there's not too many things that are going to change. So we still have this term. We have a d tau is r of the arm crossed with I dl vector crossed with b. Now, here we had an explicit form when we were doing this for a circle. We had an explicit form when we had a variable that we could integrate over, because we described everything as this single parameter phi that makes sense to use as a single parameter to integrate over when you're talking about a circle. But now we have no such thing. So the question is, what do you do instead? So this is my r of the arm. And the question is, what do you do instead? Well, we're going to say that dl vector consists of two components. It's going to have an x component, and it's going to have a z component. And then once we have that, we will integrate. So we will integrate to get the torque. So we'll get the torque is the integral over d torque, which in this case would be the integral over something with a dl vector. And the question is, how do we write this dl vector? So the question is, what do we use for this dl vector? So before, we had a dl vector which contained of components that we got by taking the position vector and then dividing it by a parameter that we were going to integrate over, and then multiplying that by d phi. But this gave us some kind of a function that was describing the way that the vector components of the position change when you move with by sweeping some kind of a parameter phi. But the cool thing is, you don't actually need to know exactly how it changes. You can say, you know what, I have some kind of a position, and that is r, and it's a function of L. And as I have a single parameter L that runs from, let's start here, 0 to whatever this circumference happens to be, I describe all the points on this wire. So I can say, well, that means I have some x component with some kind of a, some x component with some kind of a function based on L, and that is giving me the x component, and I have a y component, y hat, and I have some z component, z hat. And you add these, and now you have your position as a function of L. I didn't actually specify what that function looks like, so this sounds like a distinction without a difference, but this is actually the clue, because that means that an infinitesimal change becomes dl vector becomes the differential form of this. So that's the dx, which is still a function of L, but now, in the x hat direction, plus a dy in the y hat direction, plus a dz in the z hat direction. So we didn't actually specify what these functions are, but we do know that we can take the derivative and multiply it by something, and then we can integrate it. So that is that dx of L is taking the role of this thing, for instance, for when we were having the x component of the circle. And this dz of L is taking this role. So except now we're not specifying what that thing looks like. Oh, and of course, times this d phi and r. So we can just write this as dx of L and plus dz of L. Okay, so meanwhile, back at the torque. So R of A. Now R of A is this vector that points from here to there, which happens to be the x component of this very same, the x component of this very same position vector. So this is x of L times x hat. So that's R of A. So again, I haven't really specified what that function looks like, but I'm saying what it is. Times I, dl vector. Now we have a dl vector, that's this thing, so not a plus. dl vector, so that's a x hat dx L plus z hat dz of L. Okay, so that's this middle part, and then we cross that with B. And B, in this case, was also in the x direction. So that's B x hat. Okay, now we have this monstrous triple cross product, and in fact there's an expansion in the middle, except you'll see that we have an x hat crossed with an x hat, so we know those two are going to disappear. So all we need to keep, so this one, so crossed with x hat is 0, so therefore we drop this. So we have an x L x hat crossed with I, and now we have a z hat, running out of space here, so z hat dz of L crossed with B x hat. Okay, z cross x, so there we go, z cross x, so x, y, z. We go in this direction, x cross y is z, y cross z is x, z cross x is y. So z cross x is y. So this becomes dzl times b times y hat. And now we have an x crossed with a y is z hat. So we have an x times L, and we have x cross y is z hat, so that's going to come all the way at the very end. And we have an dzl, so I'm going to write this, that's dzl. And then we have an I and a B, so B and an I, and we have a z hat. And I think that's all the terms. Let me see. So my dzl went here, My B ended up here. My Y got absorbed in the Z with the X hat. We have the X here, I here. Yeah, I believe we've got this. Now, this is a really cool object. So this thing, I'm going to draw in this. So we have some kind of a DL vector. So let me draw it here. Okay, so we have a DL vector. I'm drawing it exaggerated. And my my X of L is this. That's my X of L. My DZ of L is that part of the DL that points in the Z direction. So that's, again, exaggerated. That's your DZ of L. Take the product of these two, and you end up with a surface area. So that product gives you this surface area. And this surface area is dA. So this is dA. So now, instead of integrating over L, we can integrate over area. Isn't that cool? So we write tau is the integral of dA times b I z hat. And now this is actually, after all of this super implicit stuff, it is what I like calling the world's most simple integral. It's just the integral of dA, which is going to give you A. So this is b I a z hat. Woohoo! That is very exciting. So, in other words, this expression that we had here, I have my I and my B reversed, but it gives you the exact same A. And my other piece of paper, which I have put to the side and I cannot find anymore. Here we go. The other piece of paper here also, B times I times the surface area times Z hat. So it's not an accident. It's not an accident that this happens, because this little trick with the X and the DXL gives you a dA that, when you integrate it, tells you what the surface area is. Now, this object, the X DZL, might be a little tricky. Like, for instance, it's not too hard to come up with constructs for a wire that look like that wouldn't work. So let me give you an example of something that a priori you might think might not work. So I'm going to draw a wire. All right, so now I'm going to draw all right, and then something on the left, but let's not worry about that. So now the question is, okay, what's this going to do? Well, anytime that there's a DL here, DL vector, that means that there is a area element set up by this vector, which I'm going to draw as this blue part. That's the dA that we add to the integral. When we're executing the integral, we're taking this slice. Now the cool thing is, here we have a DL vector on the way back that is pointing down. So therefore, this X DL is negative, gets subtracted. So we start with the blue area and we subtract the red area. So we're left with only this part. And now here, we go through here. We'll go through here, we'll go up again. And that means that now we're going up again, so that dz is positive again. And now that means we're needing to add this part, and then let's forget about this part because it's too tiny. So you'll end up with the net effect of two areas. This piece gets added, and this piece gets added, and this part gets subtracted. So this is minus, this is plus, and this is plus. So therefore, even for really, really super complicated structures where we might have several crossings at the same arm, the signs will work out to give you what the exact area is that you need to factor in. I think this is so cool that that actually works. I hope you recognize that keeping things general, even though there's usually a little bit of jumping through through mental blocks, like, okay, how can you even do this? How can you even get here? It really does work when you do this. Okay, after this little bit of algebra, where we didn't actually do any algebra, let's look at what happens with this thing when it starts to turn. So we did this explicitly before. What happens is we had this loop and it started to turn, and many things changed, but some things did not change. And really, all we need to do is we need to look at the x component. So when this loop starts to turn, that part of the loop that's pointing in the x direction starts to initially point in the x direction, but then starts to develop a y component. And so that means that there's a x, y, and z. So what we need to modify is the x component. So that means that this thing is going to become smaller because there's going to be a y component added. So we also need to add a y component, dy y hat. So this thing and this thing together will carry the angle of rotation information. And that means that we need to carry that forward throughout our calculation. Now this second term in the y hat direction ends up not doing much because there is this, where's my DL? Where's my y? Yeah, that one ends up not giving you any contribution to the torque because it integrates out. But this part is going to keep the angle information. So this thing becomes proportionally smaller as this thing rotates. So there's a rotation that goes like this. And if initially the angle, it's called initially theta is 0, then this x component becomes multiplied by the cosine of theta, and that follows all the way throughout here, and we'll end up with this term that is also multiplied by the cosine of theta. And that's not necessarily introducing anything that you haven't seen before, except I kind of threw it on top. This thing was hard enough without it. All right, can you guys still hear me? Yes, okay, thank you. Okay. So, all right, so let's see what happens when this thing starts to turn. So we have this loop, and the loop is initially initially has this orientation. So now we're looking at a top view, and we've done this before. So there's a top view of this wire. The current flows in this direction, and there's a let me see, this is the B field. this is the y direction, this is the x direction, and z is pointing out at you. And as this loop is turning, it's turning this way. Okay, so we have this loop. It's going to turn, and it's going to turn in this direction. So at some point later, it's going to have rotated by this angle, and we call this theta. And we know that the torque, it's maximum here, but when it comes and it's pointing in this direction, the torque is 0. Now, this torque being 0 means that when we go through this point, that the torque is actually going to be pointing it in the opposite direction. So now the torque is trying to turn it in this direction, but once we are here in this direction, we've gone through the 0. So our torque here, cosine theta, we've gone through the 0 where theta is pi over 2. So in this case, our torque is actually going to try to push it in this direction. So there's something very particular about this orientation. And this orientation is in fact the orientation with the lowest potential energy, because there is associated with a rotating current, there's a normal that is pointing in this direction here, and it's pointing in this direction here, and that's the normal to that surface, right? So this thing is in a plane, and there's a normal. And we choose this normal that based on the rotation of the current. So for this kind of current, the normal is pointing in this direction. And you see that if this is the equilibrium condition, because if we push it a little bit further, it wants to go this way, and if we push it a little bit further this way, it wants to go this way. If this is the equilibrium condition, obviously there must be something special about this normal pointing in the same direction as B. And what is that thing? Well, it is the magnetic moment. So when we have the torque here, we can write that as something, we can write this as the torque is something crossed with a B, and whatever that something is called mu, where mu is the magnetic moment, and it is equal to I times A times the normal, and this is the normal that is pointing normal to this surface, right? So the surface is the thing that carries this current, and this torque causes the moment to point in the direction of the magnetic field. And that magnetic moment, ladies and gentlemen, is actually the magnetic moment that is generated by the current, because when the current flows through a wire, it generates a magnetic field. And that magnetic field that it generates causes it to want to align in this direction. So this magnetic moment is actually the thing that causes magnetism. And the fact that this thing wants to point in the direction of the magnetic field is exactly the same thing that we were doing earlier when we had, when we first started talking about magnetism, where we said a magnetic needle wants to point in the direction of the magnetic field because the magnetic field points to the South Pole. So this is the North Pole of the magnetic moment, and this is the South Pole of the magnetic moment. And this therefore is the most basic definition of a magnet. So that's the surprise. Take a current that circulates and you will get a magnetic field. And that magnetic field will orient in a direction that the magnetic field that is external to it dictates. So this is the equilibrium condition, and if you point it in the opposite direction, it's not happy. It's equilibrium, but it's not stable. So mu pointing in the same direction as B, so mu is up and B is up, that's the optimum. And in the opposite direction, suboptimal. Okay, now the really cool thing I find about this is the fact that we haven't actually described why it must be that a rotating current must generate a magnetic field. But even without assuming that, the Lorentz force, which is where this thing started, already tells you that it needs to line up in this direction. So even without knowing that this rotating current generates a magnetic field that wants to align, the Lorentz force is already doing the work. So that's where we will end this lecture, and then we will start talking about, okay, we have a current that generates a magnetic field. What does that look like? And we will do that next class.